Problem set number 3, question number 3. So in the end, I didn't score this one because I realized that it was poorly worded, and the times when the question used or was asking for the number of fires, my intention was actually the number of years with fires. And those two things are very different, especially for this data set. So in the end, I just threw up my hands and said, nope, I messed up. We're just not going to mark this one. That said, I thought I would at least highlight some of the key aspects of the question. So, should the final exam or your professional life ever require you to do something similar to this, it will seem at least somewhat familiar. So we have all of our years of data. It turns out there were 105 years in the between 1896 and 2017, the end of the data set. Of those 105 years, 48 of those years had fires in them. So our empirical probability of any given year having at least one fire. Now, we may have multiple fires, but that's not what we're concerned about, or at least not what we were supposed to be concerned about. Our empirical probability for a given year having at least one fire is, because it's an empirical probability, it's a ratio, the number of things we care about over total number of things. So we have 48 years with fires divided by a total of 105 years. That gives us our empirical probability of about 46%. The rest of the questions are dealing with the number of years, or again, what the questions were supposed to be. We're dealing with the number of years that would have fires. So having calculated our empirical probability and having a fixed number of years that we were considering, so the question restricted us from 2001 to 2017, so 17 years in total. There's a fixed number of attempts, and we're looking for probabilities. That kind of points us to the binomial distribution, especially as opposed to a Poisson distribution, where we won't have that upper bound. So question number 2, or part 2 here, for instance, was exactly 2 fires. So for all of this, just to simplify it, to simplify the calculation, since I have this in Excel, I just wrote down the number of fires. And in the binomial probability, I have the binomial equation, or the binomial formula in Excel, the binom.dist. H6, this is the number of fires, and I2 is the total number of attempts. That was 16 years. H2 is the probability of getting a fire, so we had calculated this earlier, and false is always false. We do not want a cumulative probability. So this calculates the probability of having no fires out of 16 years when the probability of a fire in any given year is 46%. And so it's a very small number. And we can see how those numbers change. So it's the same equation. We're just changing the number of successes, the number of fires we could have in each year. So for this particular question of exactly 2 fires, we can look at the exactly 2 fires and pick it straight out of the table and see that it is a small number. The probability of less than or equal to 4 is the probability of 0 plus the probability of 1 and 2 and 3 and 4. So if we add all of those guys up, that is the probability of less than or equal to 4. It says 0.076 and our sum is 0.076. Same thing for greater than 10. We can take, or greater than or equal to 10, we can take 10 and greater than, because we have a fixed number, we can actually do this. And we see it's about 14%. And lastly, the probability of there being between 5 and 10 years with fires is the sum of between 5 and 10. So that is that. The expected number of years with fires. So up here we have the probability of any given year having a fire, but now we want to know, well, how many years with fires would we expect out of 16 potential ones? So here we're looking for the number of years with fires that has the greatest binomial probability. So we just look, we see that has the greatest probability, so that gives us 7 years with fires. So that is our expected number of fire years. Now that said, if we look in the actual data set, we see that of the 17 years, there's actually 16 years that had fires. So that's a pretty big discrepancy. And I think the last part of the question, again, kind of a interpret the numbers, think about what you're doing and relate it to something else, to a bigger question, saying, well, if we expected 7 years, but we observed 16 years, is that reasonable? And if we look at the probability of getting 16 fire years, when the probability of getting of any year having a fire was only 45%, we see it's a really small probability of having 16 years out of 17 years with fires. Such a small probability that we may question whether or not the assumptions are true. And in this particular case, as quite a few of you pointed out in your answers, the binomial equation and formula assumes that the probability of fires are constant over time. And that is probably not true. If we haven't had fires in a while, then maybe stuff burns more readily, and maybe there's more years with fires. You could perhaps invoke climate change, and over the past 10 years things have been getting warmer, so it is getting more and more likely to have fires. Ultimately, we don't know why things might be changing, but the fact that we got such an extreme event with such a low probability suggests that our kind of original assumption that this probability is true is probably not